So the last time we explained the reactions of the alkenes, we explained how the carbocation is going to be formed. Remember that the double bond which is in the alkene consists of two carbon atoms. Once you break one of the double bond covalent bonds, it will change into two electrons. These two electrons are taken by one of the carbons only, so that it will help the electrophile which is coming to it to make a reaction. You know that with this carbon atom, one atom will be coming which has no electrons, and it is looking for the negative charge. So for example, the H of an HCl will bond with this one. This H is coming as a proton without electrons. That's why it will interact with this carbon. Now this carbon is left with only 3 electrons. So as a revision we are doing for the last part, there is an H here, H here, H here, H here. Now this has only 3 electrons in the outermost shell of 4, so it will be plus. We call this a carbocation. A carbocation is like the cation of the metals, which it loses 1 electrons and forms a positive ion. So this one is an unstable intermediate. It should react with another atom, for example, a chlorine atom, or let's say a chloride, because this chloride will contain 2 electrons and it will make a bond which will make the final product. Until this step happens and the 2 electrons come to interact with the carbocation with the positive charge, there will be a carbocation which is formed, which is an intermediate. Intermediate, which means that it is not a reactant and not a product, is something in between them. The intermediate will react to form the final product, but until then it will stay for some time. So it depends if it is stable or unstable. If it is stable, it can stay for a while. If it is unstable, it cannot stay, and it should make the final product fast. Both of them will make the final product, but the intermediate, which is unstable, must do it very fast. If I have one reactant which has 2 options of different carbocations, as we explained the last time, if you have 3 carbons, for example, then I have 2 options here. The carbon will be attached to the H, and this one forms the carbocation. This is option number 1, and the other carbon might be the carbon that's connected to the H, and this one forms the carbocation, so this is option number 2. So both of them are intermediates, both of them will interact to form the final product, but for the time being they are unstable and they should form the final product later. So I have to look at the stability. Is it stable or not? Why are you looking if it's stable or not? You said anyway they are going to form the final product. Yes, because if it is stable, if it is by any chance stable, then there is a bigger option that this option is the one that's going to form the major product. Why? Because it is more stable. So I will imagine that most of this intermediate will form the final product, while because it is stable, while this one is unstable. So I don't think that there will be a lot of these intermediates that makes the final product. That's why it forms the minor products. So at the end, after this one is removed and the H plus is removed and is connected to a Cl, for example, and is connected to a Cl, then this is going to be the major product here because it was stable. It has ability to wait some time until it forms the final product, but the other one was unstable, so it was the minor product. But how can I know if it's stable or not? We explained last time that it depends on how many alkyl groups it is connected to. If you forgot, we explained that the alkyl group, or what we call R, is just an alkane which has lost a proton or lost a hydrogen. So it lost a hydrogen, not a proton, a hydrogen. So if you have a CH4, which is a methane, by losing one hydrogen atom, this methane is going to form, by losing one hydrogen atom, this methane is going to form what? A CH3, which is called a methyl. This is a first example of what we know as the alkyl. So the alkyl is formed from alkene by losing hydrogen. So what if you have C2H6, C2 multiplied by 2 is 4 plus 2 is 6. So this is an ethane. This was a methane. Loses an H, so it forms C2H5. This is the ethyl or ethyl. So this is the second type of alkyl. Again, if I have three, so I have a propane. If you lose hydrogen from this one, it will be C3H7. That was C3H8. And this is propyl. So this is the third example for the alkyl. Now let's see, the carbocation is attached to how many of these? So if the carbocation is attached to one, or it is attached to two, or it is attached to three, one or two or three, what? Methyl or ethyl or whatever type of alkyls. So if it is attached to one alkyl, so what is the rest? If it is attached to one alkyl means the rest is hydrogen. So this is the carbocation is attached to only one alkyl group. It's going to be called a primary carbocation, and this is relatively unstable. While the secondary carbocation is which the carbocation is attached to two alkyl groups and one hydrogen only. But if there is no hydrogens and they are all alkyl, is going to be the tertiary carbocation, and this is the most stable one. So the most stable is the tertiary carbocation. The second after it is the secondary carbocation, and the primary carbocation is the least stable one. I mean, when I'm speaking about stability, is the intermediate. But why these alkyl groups matter in the stability? The positively charged carbon atoms becomes more stable because these alkyl groups are electron donating groups. So the alkyl group is electron donating. What is missing from this carbocation? It's desperate to find one electron to replace the electron that it has lost. If it has one alkyl group, then this alkyl group donates electrons, so it stabilizes the carbon until the final product is formed. And now if we have two, so you can imagine that the stability will be more because two electron donating groups are there. And if it is tertiary, it will be the most stable because there are three of these alkyl groups. And we said that the alkyl groups are electron donating. That's why if there is more alkyl groups, it will be the most stable, the tertiary one, then the secondary. And the least stable contains only one alkyl group, so the stability is not very high. This also is known as the inductive effect. So there is an inductive effect of these alkyl groups, which we can show by using arrowheads on the bond. So I can draw some arrowhead on the bond going from here to show that this makes stability for the carbocation. Inductive effect means that they push electrons away from themselves towards a positively charged carbon and causes the carbocation to become less positively charged, That's why it becomes more stable. This means that the tertiary carbocations are the most stable because they have three electron donating alkyl groups that energetically stabilize the carbocation by pushing electrons towards it and makes it less positively charged. So what does this Markovnikov rule tells us? It will tell us that if you have a chemical reaction from the type of addition that you explained for the alkene, and one of the intermediates that formed by the interaction between the electrophile with the double bond. So we remember that we said a double bond and attach it to it. Here I have one hydrogen. Here I have only one hydrogen. and I have an H triple H here. So you said that there is an electrophile which is coming due to the breaking down of the bond between the hydrogen and bromine, and the bromine takes the 2 electrons. So this one becomes positive. Now draw the arrow, as we said, from the double bond to the hydrogen, not from the hydrogen to the double bond. The arrow always comes from the direction where there is electrons, not from the positive to the negative. Don't make a mistake by drawing the arrow like that. This is totally wrong. The arrow has to be drawn from the double bond to the H. Don't draw it from the carbon. If you do from the carbon to the H, it is wrong also. It has to be from the double bond to the H. And don't draw it from the double bond to here. It's also a mistake. So 3 mistakes avoid. Avoid drawing it from the carbon. So avoid drawing the arrow from the carbon. Avoid drawing the arrow to the bond. It should be to the hydrogen. And avoid drawing the arrow from H to double bond. It should be the double bond to the H. These 3 mistakes that a lot of students do in the exam, and they don't imagine that the person who is marking the exam will give them mistakes for these small mistakes. Okay, so I have the electron each CC double bond and the arrow coming from it, and here don't forget the arrow that shows the breaking of the covalent bond. So the electrophile, the one which is looking for the negative charge, because it is only a proton, it's a lonely proton, it has no electrons to make bond with, will interact with the electron each carbon double bond, and it will add to the carbon to make the carbocation. We said that there are 2 options of making the carbocation. Either the first carbon on the left makes a bond with the H, and the right one on the of the double bond becomes positive. Why it's positive? Again, because you have taken electron from it. The electron that was here in the double bonds are both went to the hydrogen here. So you have here H and H now. You have to make the angles correctly now. And there is H. This is the first carbocation that is formed. And you can see here that there are 2. You can see here that there are 2 alkyl groups. So there is one CH3 and one CH3. That's going to be a moderately stable carbocation, because this inductive effect gives electrons from these alkyl groups to the positively charged carbocation and makes it feel that it is less positive. So it is a secondary carbocation which is somewhat stable. This is still an intermediate which must make its transition to make the final product. The final product will come by the next step when the PR comes with its electrons and make the attack on the positive. So this goes to the positive here to make the final product that will be CH, H, H, and C and H, and here there is the PR, for example. So CH3, now this is my final product. I can see that this is a methane propane, and at carbon number 2, I can see that this is 2 propane. This is different from what's happening if instead of the hydrogen attacking this carbon atom, you see that hydrogen is going to the double bond. So there is another option that will be formed, is that the don't forget the arrow always comes from the double bond. Nothing changes here in the how it looks like, but now it will be a little bit different. So let's make it smaller so we can see both of them at the same time. Now this carbon and carbon, the carbon on the right is what's going to get the hydrogen. So the carbon on the left is what's going to be plus. And this one stays the same without change. So the carbocation is formed here by this carbon, not this carbon. So now, how many alkyl groups do you have around this carbocation? This one has only 2 hydrogens around it and one big carbocation, one big alkyl. So this is the alkyl which is C2H5. So C2H5 and 2 hydrogens. So this is primary. It's primary only. Why it's primary? It has only one alkyl group around it. So this is a primary intermediate or primary carbocation, which is going to be a little bit less stable than the secondary one, because here there is only one alkyl group which is donating the protons or inducing the electrons, the electrons towards the carbon and makes it feel less positive. So it will be less chance to get this intermediate. It's unstable intermediate. There's less chance that this will go to form the final product. And you have to notice that the final product is not the same, because here, if you add the PR later, the PR will be attacking here later. So don't forget that the PR comes with its electrons and form an attack here on this plus later to form the PR. So here, this halogen is going to be different. Even if you try to name to make sure that it is different, not the same compound, you will see that it is attached to number 1. So it is number 1 carbon. That's why you will not call it 2-bromo, you will call it a 1-bromo propane. Now it's very obvious from this rule that tells us that the chance of this happening is much, much bigger than the chance of this happening. So the chance of formation of the 2-bromo propane is much bigger than the chance of formation of the 1-bromo propane. So this is the major product, and this is a minor product. It will be very nice if you draw the mechanisms of the reactions and draw it correctly in the exam to explain that you know what you are talking about. I can say that the Markovnikov rules help us predict what is the product or what is the outcome of the addition reaction and which will be the major product and which is the minor product. It's not only in the HBr, it's in all the types of addition reactions we have explained. In the halogen halide, it will be the same also. So the halogen ends up bonded to the most substituted carbon atom. And we'll see other examples later for different types of addition reactions, how they will be affected.